This is an interesting equilibrium problem that has a lot of nice chemistry in it. We're dealing with two compounds. They have the same formula, but their structures are different. They're structural isomers. This is cis-stilbene, and it has its two benzene rings right next to one another up here. But these benzene rings sort of repel one another, and if you have some photons of light, that will break this pi bond of this sp2 hybridized carbon, which have two carbons here. It's a good thing you've learned some organic chemistry. And this carbon will flip down and then reform the pi bond. And if you have some cis-stilbene, which is a liquid at room temperature, and have it in some bright sunlight, it'll solidify to make this. This has larger LDFs. It's a longer molecule, and we can have more sloshing of electrons, so this turns into a solid. They've got the same molecular formula, C12H14, but they're very different substances because of their structure. That's one of the interesting things about organic chemistry. We have so much of structure determining the chemistry of substances. But let's deal with equilibrium now. In a nonpolar solvent, we make a solution, and these two can do their equilibrium thing. And they're saying that the equilibrium constant, in this case concentration, because we've got it in the solution, for the system is 24 at room temperature. One form is favored since the benzene rings are sterically hindered in the less favored form. They're saying, okay, these guys are hindered, they're bouncing into one another. This is a more relaxed version of the trans-stilbene. If you look at the equilibrium expression, we always have products, the trans in this reaction, above the reactants. That's our arrangement. We know the equilibrium constant is 24, so there's going to be 24 times more trans-stilbene than cis-stilbene in this. You expect to have a lot more of trans, first because it sort of makes sense in terms of structure, but the equilibrium constant confirms that. The bigger your equilibrium constant, the more likely you are to have products. Using this information, which equilibrium concentrations would you expect? Well, we'd expect more trans over cis. Now, here we've got a problem. It's not going to be the same as the problem in WebAssign. It's got a different concentration. I generate random numbers for these problems. And we have cis-stilbene initially present. We just made some cis-stilbene. There's nothing else. And has a concentration of 0.705 millimoles per liter. 0.705 millimolar. Calculate the concentration of each of the isomers at equilibrium. Well, let's see. We start off initially, we love our ice charts, with 0.705 cis-stilbene. We've said that we don't have any trans, so we know this is going to be 0. And we know there's going to be some changes. The reaction is going to make some of this trans, and indeed, that's going to be the minus X. And we're going to take this cis minus X and convert it into trans plus X. Love that X. René Descartes popularized X and Y and Z for unknowns back 400 years ago. He also set up A, B, and C for known quantities. But let's use our X here and realize that there's going to be 0.705 minus X cis-stilbene. That's going to be reduced, and we're going to get X amount of trans-stilbene. So we've got ourselves something that we can solve. We can find out what the equilibrium concentrations are going to be once everything is taken care of. So we set up our equation. Gotta love algebra. 24 is equal to, that was our constant, that this is going to always equal, no matter what number you have here, X divided by 0.705 minus X. We can multiply both sides by the 0.750 minus X, and then do our algebraic thing. But I thought it might be fun to try and use Solver. If you paid some money for this calculator, you might as well get some use out of it, and using Solver is always fun. So I'm going to go to Solver, Math, and it's the last in that scroll, so I can just move up, and there's Numeric Solver, and I'm going to say we're going to have 24 that we're going to be shooting for, and to do that, we're going to go through this function where we take, they have an x here. Isn't that nice? X divided by, don't forget your parentheses, 0.705 minus x. I'll close the parentheses, make this look good. You can do second function solve, or right underneath here it says OK. We just hit that, start at 0, and then have it solve this. Let's see. What are we going to get? Ah, there's it. X is going to be 0.676. So that's going to be our x. Let me bring that up again. It sort of makes sense. If we're starting at 0.705, we're going to lose most of it. Our minus x is going to be 0.677, 3 significant digits. So let's go further down and answer the question. Our equilibrium, most of our cis-Stilbene has changed into trans. So how much cis-Stilbene do we have left? I'll pull my calculator up again. And one of the nice things is once this is x, you know it's x. So I'm going to go back to the main window, quit here, and say I started off with 0.705 minus, I didn't have to remember that because I know this is going to be x, enter, and that's all I've got left. I've got 0.0282 millimolar of trans, and of course, our x here, in case I forgot it, is 0.677. So I'll put my answer here, 0.677 millimolar. Indeed, we've got a lot of our trans. This stuff lined up, so it's London dispersion forces can make those temporary dipoles, and very, very little of this cis-Stilbene. Let's double check. I always like sort of doing that and see if this does make sense. If we take our 0.677 divided by 0.0282, this should equal 24. We should have 24 times more trans than cis. 24 all the way out to 3 significant digits. So we've solved this problem. We used algebra to help us and also a Texas Instrument. You might try doing this algebraically to see if you are as smart as your calculator.